Hi, everybody. Welcome back to our Astro Coffee Hangout for, I think this is going to be our last one for 2017. Today we're going to be talking about black holes, and in particular, the black hole around the center that is located at the center of our Milky Way galaxy called Sagittarius A star. Now, you guys have been around long enough to know that black holes are not only really interesting, but they are also rather not a good neighborhood to build a home. Let's just put it that way. The real estate around a black hole can be somewhat turbulent, but it wouldn't occur to, at least it didn't occur to me, that would be a very good place for stars to form, or that it wouldn't even be possible for stars to form. Well, today we're going to be talking about the idea that, well, these astronomers they've been looking into this, have recently published a paper that show that stars can form near a black hole, in particular Sagittarius A star. And we're going to be talking about that, with their results with them today as we head into today's hangout. So, but without any more ado, let me go ahead and bring up my Astronomical Brady Bunch group, and let me introduce my co-host, Dr. Carol Christian from the Center for Emerging Media. Hi, Carol.
Hello.
Hi, you want to introduce our hangouts to people?
Sure. Afternoon Astronomy Coffee Hangouts, as some of you know, and hopefully some new people are joining us as well. It's like a science coffee at my institution and most of our universities, where we sit around and chat about the current research, and we have a dialogue about it. Sometimes we're fortunate enough in our universities to have a speaker who's going to give a colloquium come and chat with us too. And we thought, wow, it's such a nice experience when we're doing research to learn about what other people are doing and get behind the scenes a little bit about what they were thinking, how they took the data, what happened when they got the data, and how they arrived at their conclusions. And that's what we're doing today with our scientists. And this hangout is sponsored by the easy for me to say, American Astronomical Society and the American Astronautical Society.
Oh, good. I'm glad I made you say
and we
that
are very grateful for them supporting us and being able to bring coffees to you. So grab your favorite tea, coffee. I'm drinking sparkling water, and whatever beverage, and join us and join in the conversation.
All right. Thank you, Carol. And also joining me is my good friend Carl Clark. He's going to be helping out in the hangout here. In particular, he's going to be looking at the various social media streams that we're broadcasting on right now, including YouTube, Facebook, facebook.com/deepastronomy, as well as Twitch and Periscope. So he's looking at all of that. And if you want to just tweet us on Twitter, then use the hashtag AstroCoffee, and Carl will see it, and he will either interrupt us to ask a question if it's relevant at the time, or we'll have some time at the end of the hangout where we'll go over all that stuff. So welcome, Carl. It's good to have you back. And let me also introduce our guests today. So let's see, going from, I think I'll start with the upper left, is Dr. Al Wootten. He is a astronomer at the National Radio Astronomy Observatory. Hi, Al. Welcome. Also, right next to him in the center there is Dr. Mark Wardle. He is joining us from very far away in Australia. He's at Macquarie University there. Thank you for joining us at such a interesting time for you. I know you're awake though, right? Because
yeah, no, I'm fully alert.
Yeah, you're right.
I really appreciate this. I really appreciate it.
That's right. And also Dr. Farhad Zadeh from Northwestern University. Welcome,
That's
Farhad.
Me.
It's good to have you here. Okay, who wants to give us a summary of this paper? Because first of all, most of us know what a black hole is. I think most of us know that that astronomers believe that around almost every galaxy in our universe, there is at its center a supermassive black hole. And these are black holes that are on order of 100 to several 100 million times the mass of our sun. So these are not your tiny run-of-the-mill little black holes. These are huge, supermassive, as they say. And they're everywhere. They're in all the centers of most of the centers of most of the galaxies. But you guys, and now they're known for sucking things in, right? But they destroy, they devour almost everything that comes near them. But here you've been looking at the one at the center of the Milky Way, and we've got a name for it. It's called Sagittarius A star, and you found that some stars are forming around that. Is that right? Who wants to give us a summary? Either
well,
one.
I could give you just a quick summary of what we found. In fact, it's interesting that the first time that we looked at these sources, I was in Australia, and we just had ALMA data that we had just taken. And it was a very nice coffee shop, and I was sitting with Mark, and I said, "Look, Mark, let me show you this. This is just amazing." And then we were stunned that there is a bipolar outflow, which is really a great signature of low mass star formation. And it was just one source, and then we looked more, and I looked more, and we found 2, and then 3, and then 4, and it just continued on. And we found a whole bunch of them. The first one that we found was it's called bipolar 1, and you see in this image. So the black hole is where we see Sagittarius A star. There's a cross there. And then bipolar 1 is just a little bit to the right. And you see basically 2 lobes. These 2 lobes are expanding with a very sort of a low velocity, low speed, but the 2 lobes are moving at about 115 kilometers per second. And that's huge in terms of the velocity of the 2 lobes. But then, you see this one side is blue shifted, meaning that it's moving towards us, and the yellow component is the red shifted component, and is coming towards us. So these are really interesting signatures, very interesting signatures that you find whenever you find a protostar that is sweeping its material and cleaning up all the dirt and material that surrounds the protostar. So that's one of the sources that we found. Yeah.
So one of the ways you can tell a star is forming, I mean, not just around a black hole, but anywhere, is this what you're calling them, bipolar lobes. These 2 blobs here. When you see those, you say, "Hey, a star is forming."
Well, it has to have both the right size, the right shape, the right velocities, and when you know where the object is located. And if you see these 2 lobes, the blue shifted and the red shifted lobes, moving from a central source, and we also found the central source at the center of these 2 lobes, then you know that you have a protostar, and it's at its very early phase of star formation.
Okay, and Mark, do you have anything you want to add to this image here, or to the summary?
I think, as Farhad said, we were kind of very surprised to see this so close to Sag A star, just because of the nature of the environment there. It's not that close in. You don't really expect stars to form out there.
Okay, well, what are we looking at with distance? I see Sag A stars right here in the cross. The x-axis is in arc seconds, so we're looking at something around 15 arc seconds to the right of it. But I mean, how far away is this from the black hole?
25 arc seconds is a parsec, so you're looking at a couple of light years.
So maybe like 0.6 of an arc of a megaparsec then, or something like that.
No, parsec.
Just parsec, not megaparsec. Sorry,
parsec. Yeah.
So what did we know about the environment of Sagittarius A before? What did we think it was? What did we think it was like before you were discovering star formation there? We knew there was stuff, but what kind of stuff?
Well, we had found some indications that young stars are forming there in the last several years or so. And but it was never really conclusive. You couldn't really say for sure that this is just a signature of star formation. And then I think you could always explain those with a different sort of mechanism. But this one, this sort of population of bipolar outflows that we see now, all close to within a couple of light years of the black hole, they're extremely difficult to explain it in any other ways. So this was really turned out to be a very conclusive way that we see star formation taking place. Young star formation taking place, and they're actually low mass star formation, stars that are as massive as the sun. So when it was actually much earlier in its earlier phase. Perhaps Al could add a little bit more on this if you have.
Al, you have something to add?
Yeah, right. Well, so when you look at anywhere as far away as Sag A star, 8,000 kiloparsecs, 8,000 parsecs or so, you're going to have a hard time seeing anything but the most massive stars. So the first thing Farhad did was, in some early data, identified some of the signposts of very massive stars. And then you ask, well, how extensive is the star formation? Are there low mass stars? And they're very much harder to see this far away behind all these magnitudes of extinction to the galactic center. So he had the great idea of looking for the outflows there. I think of them as kind of like pretend you're on a beach and the lifeguard is somewhere way far away and trying to signal you that there's a shark coming. He has little flags and might wave them around. It's like a semaphore. And the bipolar flows act the same way at the galactic center. They make the star, which ordinarily be very hard to see, much easier to spot just by the fact that they've got these, a blue flag on one side, if you will, and a red flag on the other.
So is this what you're talking about here, what I've got up, these outflows?
Yeah.
Okay.
Yeah, carbon monoxide at different velocity bands stepping along, and they're color-coded according to whether the material is coming towards us or blue shifted or moving away from us or red shifted. And so you can see that in each velocity bin, the material shifts such that there are two different lobes. And in between them is the protostar. Why does it have these outflows? We think that as the material falls onto the protostar, it's rotating. And so there's a disk of material probably around the center of the protostar. In order for the star to form, it has to lose some of its spin, some of its angular momentum. And we think that's done through loss of material in bipolar outflows off the polar axis of the star. So probably what is down in the center here is a little star, and there is some evidence for a source there. There's probably a disk that we don't really see very well at this kind of resolution or distance, which is funneling material onto the protostar. And then in order to continue to form its star, the protostar has to lose some of its spin, and does that by shooting off these jets in two different directions.
Wow. So there's a lot going on in the center of our galaxy. I remember seeing a lot of animations and research about, that's plotting all of the orbits of all the stuff that, the stars near Sag A star that's going all over the place, and they're whipping around at various rates. So this is a pretty turbulent area. Now, our black hole, as I understand it, isn't active right now, because what makes a black hole active is when it's feeding on something, right? And so right now it isn't exactly feeding on something, although there is, I think, a gas cloud swirling around that might eventually fall in. Is this star that you're looking at, which is only a few light years away, is it any danger of is it going to actually make it? Is it going to form, or is it going to fall in eventually itself?
Well, no. It's on an orbit around the black hole, and it should be able to maintain it, at this kind of distance. We don't fully know what its orbit is, but we've got some idea of the motion towards and away from us from the channel maps that Al was mentioning. So it's probably moving fast enough just to keep in orbit around the hole. There's other material we see orbiting a little bit further out. This ring of gas, that's twice as far away or so, maybe 3 times as far away. And, it just maintains an orbit. So although, black holes can be scary in the sense of you always think of them pulling stuff in, and they certainly do that to some degree, if material has enough orbital motion, it will just stay in orbit.
Okay, so that's what's happening here. You think it's not gonna run the risk of falling in. Now, yeah, I've heard about this gas cloud. In fact, I've done a Space Fan News on it, where it is swirling and will probably fall in. And when it does, presumably some X-rays or gamma rays or short bursts of high energy radiation will come out of the jets that are there. How big is our black hole? Let's just remind ourselves. How big is the Sgr A star?
It's 4 million solar mass.
So 4 million. So
hole.
even as supermassive black holes go, it's actually not that big, really, is it? I mean, there are much bigger, on hundreds of millions in other galaxies. So,
That's right.
And our galaxy is a pretty regular-sized galaxy. I mean, it's pretty. Would you characterize our Milky Way as a ordinary spiral galaxy, or is it larger than most, smaller than most?
I think it's larger than. It's fairly large. It's not, the biggest, but it's.
So that's kind of weird, isn't it? That the size of a galaxy doesn't scale, or the size of a supermassive black hole at the center doesn't scale with the size of the galaxy. Because you'd think, wouldn't you? Maybe
but
not.
The size
that it would be bigger.
There is a strong relationship between the mass of a supermassive black hole and the mass of the bulge of the galaxy. And our Milky Way black hole also follows the same relationship. So you would see the same relationship. So there's somehow, what's interesting is that star formation must have been taking place at some time in the past, and also the black hole growth must have also been doing the same thing, increasing its mass, and the two are correlated with each other. And now what we really see is something very close to the black hole itself, and star formation is taking place there. And the question is that, how does that relates to the growth of the black hole? And so we're really studying also the relationship between star formation rate, the rate at which stars are being formed, and the rate at which material is falling onto the black hole. And that's an interesting implication of these type of measurements, that you're learning not only about star formation in a very, very hostile environment, but you may be able to learn something about also the black hole itself. Because when the universe was much younger, maybe at the redshift of maybe 2 or 3, the star formation rate was maximized, but also the rate at which material fell onto the black hole was also maximized. So there was a growth, the growth of the two different sort of the two different aspects of these processes were correlated with each other. So we are now learning about star formation in a near supermassive black hole, and hopefully it can also tell us something about the rate at which material falls onto the black hole. And of course, you can that may have some implications on a larger scale on other sort of supermassive black holes, and the way that they work together with star formation. Yeah.
So you're talking about early on, the black hole is growing, there's star formation going on, there's material around it, and now it's more quiescent, it's quieter, and then we see this object with a bipolar flow, and we know that's a characteristic of something young. Do we know anything about, have we seen older stars around the black hole? Do we have any measure of, as you say, the rate of star formation around this black hole? Because you've talked about two epochs, when it was young and now. Do we know anything about, can we see anything that's a remnant from in between?
Yes, in fact, we have about 100 to 200 massive stars that are even closer to the black hole than these bipolar sources that we're talking about. So but they are older. They are about a few million years older. Their age is about a few million years. And so that's also very interesting. But they are all massive OB stars that are orbiting around the black hole, and they were formed a few million years ago. In fact, what's interesting is that for for some time, people thought that these massive stars, 100 or 200 OB stars, were formed somewhere else, and then they migrated towards a black hole.
Wow.
But I think now people have studied more and more, and they realize that theoretically it is possible to explain the origin of these massive stars such a way that they're formed very close to the black hole. And of course, these measurements that we have reinforces the idea that star formation can indeed take place in such a highly stressed environment. And
well, yeah,
so
I get that you're starting to get a sense of that stars can form near black holes, but I don't see how can you tell the difference between a star that's been captured and a star that has formed near the black hole, or does it even matter? Like, how do you know it's been captured and versus having formed nearby?
Yeah, I think it's hard to understand how to capture a star unless it has approached very close to the black hole. So,
well, again, that doesn't seem so unrealistic. I mean, stars can travel close to black holes, can't they?
Sure, but then they tend to come back again. That's the problem. So firstly, the size of the event horizon of this black hole is very, very small, right? So it's a fraction. It's about an astronomical unit, something like that, a tenth of an astronomical unit.
Wow,
that's
really?
that is small. I didn't realize that. Right,
because it just a normal mass of the sun black hole. It's a couple of kilometers or something, and it just scales. So it's 1 million times bigger. But that sounds like a lot, but it's actually not on the scales we're talking about. So in terms of a direct target, it's very hard to hit the event horizon if you have something that's just passing close by. And then if you want to somehow slow it down and get it into a very tight orbit, you have to kind of distort the star a little bit using the different gravitational forces across the star. You have to be very close for that effect to happen. So at these kind of scales that we're talking about, it's very hard to have the black hole capture a star that's really in some orbit, even if the orbit is quite eccentric and it passes relatively close to the black hole on these scales. It's really, the odds are just so slim.
So because because either things will get flung out or it'll just fall in, but getting one to get in the conditions where it's in an orbit is a pretty hard thing to do. Is that what you're saying? In
a circular orbit, I mean, it can come in, it depends how you've launched the star, where it's coming from, right? It's like things coming into the solar system. Mm-hmm. They'll be on a hyperbolic orbit and just come around and turn around. Yeah, it's all general relativity and so on, but that only kicks in if you get in within, a few Schwarzschild radii or 10 or 100 Schwarzschild radii of the black hole.
Got it.
So you have to get very close for GR effects to really kick in.
Okay.
But also, just I want to add something to what Mark said. These sources that we're finding, they're extremely young. They are less than 10,000 years old. So it also makes it very difficult for a star to be captured in having such a sort of short age.
So I know what we're talking about. We're talking about these stars that are in orbit around the black hole now, Sagittarius A star now, and you're saying they're young?
That's right. That's these bipolar outflows.
No. I don't mean the bipolar outflows. I'm talking about the stars that are already in orbit around the black hole. You're saying those
the massive stars.
Oh, those are older. Yeah.
Okay. All right then. Good. So
a few million years.
Right.
So we're seeing at least two generations of stars, sort of, schematically.
Okay. So, Carl, I'm seeing a lot of question marks. Do you want to read some of them off of the YouTube thing, or do you want me to do it?
Can you hear me? I thought I muted myself.
Yeah.
Okay, cool. Yeah, no, I will read them. Let me bring that up real quick.
Because Chuck's got a good one, and Andrew Planet, things like that. So
yeah. So, and I have there's a couple that I saved from earlier. But let's get Chuck's, because I had that. Can you elaborate on the jets showing the spin of a star during formation? Why would it not fling apart before any jets emerge? And
No, the question is, can you elaborate on the jet slowing the spin of a star during formation? Why would it not fling apart before any jets emerge? This had to do with those lobes, I think. So
yeah, okay. I think what he's referring to is the lobes, is the jets.
Yeah. Anybody? Why don't they just fling apart before they come together?
Well, you have what is known as conservation of angular momentum. So the material that is falling onto the protostar, so there is an issue that you have a very, if a cloud, as it spins and forms a protostar, were to do what it's supposed to do, the protostar would have spun really, really fast, and 100 or 1,000 times much faster because of the conservation of angular momentum. So the question is that why is it that stars are not spinning as much as they're supposed to because of the conservation of angular momentum? And it turns out that if you find a way to get rid of some of the material, eject them, then you can slow down the protostar. And nature has a way to do that by just getting rid of the ambient material in its vicinity, and it forms these jets of outflows. And these outflows are generally shown in terms of, two lobes coming out. So that's really the way that a protostar produces a jet and gets rid of its excess angular momentum. And of course, it's a subject of a lot of studies by many theorists trying to figure out basically how you get rid of the excess angular momentum and produce these bipolar outflows. But observations are there. The question is that how does it really work in detail? And that's the kind of things that people like Mark work on, trying to figure out what how this works. You may want to add something, Mark, if you like.
Oh, just to emphasize what you said, that the trick that is being played here is that the spin, the angular momentum, is getting deposited in a small amount of the gas that's forming the star, and that material takes it away and leaves the rest behind to form the star. And that's what you see when these jets come out.
But what you're saying is this material comes in and it's getting closer to this very young object, then it comes off the axis, and you're
some of it does and some of it does and some of it doesn't. So the ballpark estimate is a few % of the material gets flung back out. Certainly in the later stages. It might be a little bit more in the early stages.
And it seems dramatic because we see these jets. But I was just going to comment that these kind of outflows are seen in lots of objects.
Yeah. Many classes of objects, right? So certainly stars forming in the molecular clouds in the disk of our galaxy, of course, which is what we're using to understand the object here, but also in other kinds of objects that have disks and a central object.
If it accretes, you get these lobes. Is that it?
Yeah, it seems to be the case. That's right. So it seems fairly generic.
Okay.
But the only thing I want to add is that this is a molecular, very cold gas that is coming off. It's not a hot sort of outflows that you see in other contexts.
How cold?
These are the temperatures are about maybe 50 degree Kelvin.
Yeah, but to be fair, this is the material. So the lobes we're seeing are material that's being swept up by an underlying jet that's lower mass, but moving very fast. So it's sweeping up the surrounding material and pushing it out. And we're seeing the surrounding material being pushed out. And the underlying jet from the star is higher velocity and higher temperature, probably 1,000 degrees or a few hundred, something like that. Depends on the scale you look at.
Okay. Hang on just a sec. I just want to read David Sims. David Sims got a comment here. I love him when he's on the Hangouts because he does the math. A 4 million solar mass black hole has a Schwarzschild radius of 0.07941 AU.
Yeah, point one. There you go.
Yes, thank you, David. And no, I'm serious. He does the math every time.
Yeah. Like Mark said.
Check up on us, please.
Yeah.
Like Mark said.
Okay, go ahead.
Hesitation when I was trying to remember what it was.
You get an A+, Mark.
Yeah.
Good.
So Achilles asks kind of about the life cycle of black holes and the quiescence you were talking about, Carol. Like, would these stars only form in quiet times of a black hole's history, or do you think a more active time?
Oh, that's a good question. Yeah,
would affect the gas around it. So, like, when this gas cloud that Tony's talking about falls in and makes it an active black hole, an active galactic nuclei, what's going to happen to our nice little newborn baby?
Al, you've been quiet. Let's do one. Can you tell us that one?
Yeah. I don't think I'm the best person for that one.
Okay. All right. Well, just trying to get you into it. Okay, go ahead. Anybody who wants to? What about quiet versus active black holes and having these stars?
I think you want to have stars forming first before the black hole becomes active. That's really the key, because the minute when the black hole becomes active, then it's really chaotic, and you see these jets and outflows, and it basically disrupts just about everything around it. But if you form a star, then the chance that they can survive is a lot better. And that's they could still be simultaneous. You could have basically an activity associated with the black hole itself, and also star formation could take place. But there is a phase difference between when stars are formed, and I think it's a lot easier to form stars earlier before the black hole becomes very active.
Well, that's kind of related to what Andrew Planet is asking about. What can accretion disks around black holes? So, is that area too active for any kind of star formation to happen too? I mean, you're not going to get any stars forming in an accretion disk, are you?
It depends on the scale of the disk. So, on the scale of Sgr, for Sgr star, no. But on the other hand, we do think that the hot million-year-old stars that Farhad was talking about earlier, that they formed in a disk that could have been consisting of material spiraling onto Sgr star, but on much larger scales than the current disk. So depends how close in you're talking about.
So that's really an environmental question, isn't it? I mean, if the accretion disk is large, that means there's a lot of stuff around the black hole that's accreting, and if it's big enough and far enough away, then maybe, right, you might get clumps.
Yeah, sorry,
go ahead.
Okay, and just, you have this big difference in the mass of the black hole between our supermassive black hole, that's one of the lower mass supermassive black holes, and the ones that are 100 or 1,000 times more massive. And so there will be some big differences in the scale on which different processes occur there as well. So it does depend on a few things, which is a dreadful answer to give, but it's the way it is sometimes.
Well, yeah, and we're going to just keep our discussion about Sgr star right now, since that's what we're talking about. But yeah, there's probably other black holes with huge accretion disks where who knows what's going on in those things. Okay, any other questions you want to ask there, Carl, before we move on?
There's a couple more that came in just kind of about Sgr A in general. Is Sgr scheduled to be active before the convergence with Andromeda, and that's J.B. Smith's? And kind of a really broad galactic evolution question that I think it has to do with conservation of angular momentum, but we might not know the entire mechanism. Scarvian Vivian, yes. Scarvin Vivian, yeah. Why are not all galaxies spiral?
All right, let's go back to the first one. Those are two different questions. So, Sgr Star, is it going to be active before it collides with Andromeda? That's like 2.5 million years from now, right, or something like that? Or no,
I want to put it on my calendar.
Yeah, it's a few billion. It's 2.5 million. I always get this backwards. It's 2.5 million light years away, and it's happening 4 billion years from now. Surely, in 4 billion years. Sgr Star.
I'm busy then.
It's going to be
Say that again.
I could just say that, since we see now lots of dense clouds very close to the supermassive black hole next to Sag A star, I think it's natural that some of these materials that are not really forming stars fall into the black hole. And so you have the sort of the fuel now very close to the black hole. And if this fuel really reaches a black hole, then you have a firework, and that's where you do see some kind of activities. And I suspect that this kind of activities associated with Sag A star will happen for sure in the future, near future.
Right. Okay. Good. So
I'll also add something, if I may. Yeah.
You may.
Well, I was just going to say maybe we should mention that. As part of a worldwide telescope, the Event Horizon Telescope, ALMA did take images of the galactic center black hole in April. It takes a long time to get the data together from those. One of the big problems was the South Pole Telescope data was frozen in the South Pole until it recently opened up to visits as the summer came down there. But the data's all out now, and we should have actual images of the Event Horizon, or very close to it, on a time scale of a year to 18 months, I think.
Oh, Al, I could kiss you for bringing up the Event Horizon Telescope. I love that. So this is an idea, folks. This is amazing. Observatories around the world, of which ALMA was one, participated in imaging. This is direct imaging of the event horizon of a black hole. We're not modeling it. We're not inferring it from the effects of something else around it. These guys are trying to see it directly. And so, Al, you brought this up. We have data now, because waiting on South Pole Telescope, a little bit of a laggard. I get it. It's cold down there. But you've got the data and you're putting it together now. When do you think we might see the results of that amazing endeavor?
Well, that's a good question. I mean, the ALMA board was very interested in this 2 weeks ago. The answer is, it's going to take a while. It'll probably be next year, certainly.
And that's just because of the volume of data you've got to go through, right?
Well, it's partly the techniques had to be developed. I mean, we don't want to get too incredibly technical, but different telescopes take data with different polarizations. Some use circular polarization, some use linear. You have to convert one to another. The data rates are extremely high. Mm-hmm. I mean, the data that was collected in this experiment is probably larger than in any astronomical experiment so far. The huge volume of data. And then you have to correlate it all for each baseline. You have to sort of play back the event as it was recorded at that telescope against other telescopes, all other combinations of telescopes. And then in the end, you finally have the data from which you can make the image. So it just takes a very long time.
Well, I just can't believe that this hasn't gotten more attention than it has, because the Event Horizon Telescope is really an unprecedented thing. And I've been very amazed and excited about the work that's coming out of there. And related to this, though, I want to talk a little bit about the environment of looking into where Sagittarius A star is. Now, the Event Horizon Telescope is doing it, and anybody who's ever looked up in the night sky and looked toward the constellation Sagittarius, which is where the center of our galaxy is, you don't see a whole lot there. It is obscured from us in many wavelengths. So what is the optimum ways? And we talked that this is the topic of this hangout is ALMA data. ALMA stands for Large Atacama Large Millimeter Submillimeter Array. So that tells you the wavelengths that we're looking at. Is that what both the Event Horizon Telescope has been looking at, primarily radio wavelengths, and or I guess I'm asking, give us a sense of the environment through which we have to look to see this black hole. Anyone?
Well, optically, it's very obscured by all the dust, gas, and other stuff along the line of sight to the galactic center.
Good. I was getting to, yeah.
But there's also, and so that's why we use long wavelengths, radio wavelengths, and in the infrared, maybe you've seen the movies of the central cluster stars all zooming around the galactic center black hole. But there's also a problem with longer wavelengths, in that there are a lot of charged particles around the galactic center. And so there's a lot of scattering of the radio signals, and that gets lessened the higher you go in frequency. And so this particular experiment is very well suited to millimeter wavelengths. And so we did this at wavelengths of 1 millimeter to get around that scattering problem, because we really want to see as close to the galactic center as possible in order to try to image it.
So I want to show this image again. This is ALMA data, and this is what it looks like in radio submillimeter wavelengths of the galactic center, correct?
Yeah, this is a particular molecule, carbon monoxide.
Oh, okay. So you're looking at it as, when you say that, by the way, what do you mean? This is a wavelength that is emitted by carbon monoxide molecules. What do you mean when you say that?
Yeah. So each molecule, it's sort of like a little bell. It has certain frequencies that it will emit at, and for each molecule, that depends on the atoms that are in it. So for carbon monoxide, it broadcasts at very specific frequencies, like a bell or a little radio station. One of them at 2.6 millimeters, and then overtone. So this one is at 1.3 millimeters. There's another one at 0.8 millimeters, and so on. So the carbon monoxide molecule will emit at very specific frequencies, and that's what allows us to code the emission that we see as either redshifted or blue shifted, because we know from our knowledge of this particular region what zero velocity is. And so with respect to that zero velocity, we can measure the shift of the carbon monoxide emission and tell whether it's a little redder or a little bluer.
And that's true of everything in this image, not just that bipolar outflow, right? So
right. So this is all coded red, green, blue according to its velocity.
Right. In fact, if I may add something, if you bring back the image one more time, please.
I can't have it up.
It from here. Oh, okay. So this is a true color image, because red shows up at a velocity of 115 to 117 kilometer per second, and green 113 to 14, and blue is 110 to 112 kilometer per second. So this is carbon monoxide emitting at a frequency that corresponds to velocities, these high velocities, and that's what this is. Basically, what you really see is a cloud being traced by the emission from carbon monoxide. And that's how a molecular cloud looks like near the center of the galaxy. And of course, you see the bipolar outflow showing up just at the southern part.
I know it's very bright in this image. It's really unmistakable. How?
And remind us why we use carbon monoxide as other molecules. You look at other molecules as well.
Well, it turns out carbon monoxide is an excellent tracer of molecular hydrogen, which is, generally dominates the interstellar medium. And that's why you rely on carbon monoxide.
I mean, carbon and oxygen.
Yeah, go ahead.
I was just going to say what you're going to say. The abundances are very high. Carbon and oxygen are among the most abundant elements in the universe. So.
Okay, let's try to, you want to get to some more questions, Carl? Do you have anything handy?
Yeah. There's actually two really good ones. So Condor Boss, love the name. Are any of the stars in orbit around Sag A likely to spiral close enough to suffer tidal disruption, or is the environment quiescent? I love that word. I'm going to use it from now on.
Hello?
Yeah. Well, I could just add a little bit. I mean, I think one of the most interesting aspects of these observations that we've had is that why do you have a star formation near a supermassive black hole that has a very strong tidal force? So you really, the tidal effects tries to disrupt clouds, and yet these sources seem to be showing up, and you have a collapse of a cloud. Why is it just collapse taking place? You have a battle basically between the tidal effect that is trying to disrupt the cloud, and you have also self-gravity is trying to compress the gas and form stars. And you would think that the tidal effect by supermassive black hole should dominate and should really win the war. but these sources that we see suggest strongly that self-gravity can actually dominate and form stars. And I think it's just a matter of the environment that these clouds are in. If you have a source of pressure, external pressure, and this external pressure can actually help self-gravity, and collapse could take place. And I think that it all depends really what kind of environment these clouds are moving through, or even as stars moving through. And the tidal disruptions could happen if there is no external pressure. And if it gets too close to the black hole, it should just completely get disrupted. However, if you have an environment which is fairly has a very high pressure, this pressure can actually help the survival of the cloud not to get disrupted as it gets close to the black hole. So that's what we really see in the sort of the two forces that are constantly, there's the tug of force going on. And I think that's in these cases, star formation happens when one self-gravity basically wins over the tidal effects, and it's because of the environment.
Yeah, I can see that being a very particular situation. Depending.
Well, if anybody, Mark or Al, if you want to add something more, that would be good also.
Well, just that the pressure in the central region, the interstellar pressure, if you like, is much higher than in the disk of our galaxy. And so this is an environment where, when you're thinking about the conditions under which clouds might collapse or be torn apart, you have to take that into account. And that's the reason that we think this low mass star has managed to form, is that a dense enough cloud has been able to form close enough in that will then collapse.
Galaxia, you're back. It's good to see you. She didn't understand something you said. I think it was Farhad, that you were talking about the scattering gets less near Sagittarius A star at what frequency? I think you were talking about the high energy scattering.
I think Al was.
Oh, was it Al saying that? I'm sorry.
Yeah.
I'm sorry.
Yeah. Okay.
What frequency was that? Where the scattering gets less?
Well, just as you go higher in frequency at low frequencies. I mean.
Oh, I see what you mean.
We could take an image of Sag A star with existing centimeter radio telescopes. But the trouble is, when you try to do that, you don't quite see all the way in. Instead, you see the image is fuzzed up by the fact that the radio waves are scattered by electrons and charged particles in toward the center. But that scattering is lessened as you go higher in frequency. And so it's much less at 3 millimeters and far less at 1 millimeter. So the experiment was taken at wavelengths of 1 millimeter.
Okay. So, yeah, thanks for clarifying. Just real quick, I want to ask Achilles' question. He goes, have you done any calculations or simulations at the star-forming rate that Sag A star could produce based on this finding? And how does that rate compare to what we know about the Milky Way star rate? So you found one star. It appears to be forming around the black hole in the center of our galaxy. Have you done any calculations or simulations about what this might mean for the star forming rate of around this black hole?
I mean, there are uncertainties. We've got more than one of these objects. There's about 10 of them. And we think they're 5,000 to 10,000 years old, something like that. So you can say, okay, if you assume, a solar mass or half a solar mass, and you can multiply things up to get some rate. I mean, it's a very uncertain estimate, right?
Right. But, yeah, I get that, because you've only got a few data points here to work with, right? So
yeah, and so when I put those numbers in, I got about 1,000th of a solar mass per year, whatever that means, right? Which is not a huge. Or if you want to do it over the lifetime of the galaxy, that's equivalent to 1 million solar masses per billion years, which is a more interesting number. It's a kind of a wild extrapolation to go from these 10 stars that tell you something about the history over the last few thousand years to a billion-year timescale. But
Right, because I mean, I think here the real amazing thing is that you found stars that can do this at all, that they can form near black holes. That in itself is, I think, the real amazing thing here. Do we know what the star forming rate of our galaxy is right now? How many stars are formed per year? Do we know?
I think it's about 10 to 20 solar mass per year.
It's quite a bit. I mean,
or
it's
even
a lot
less, maybe about 5 to 10, something like this.
Yeah, so it's a lot more than what you would expect based on these observations here. So anyway.
But as we were discussing before, there are these more massive OMB stars which formed before, so that's another data point.
Yeah.
That's right. That's exactly right.
That's
Right.
That's
So there has been something going on.
Yeah, and that actually gives you a similar number for those kinds of stars as well, actually.
Okay.
So
And
what
remember-
people,
Just in terms of the total rate in the galaxy, remember we're looking at a very small region of the galaxy here, to be fair to it.
Yeah, but that doesn't prevent us from wildly extrapolating.
Oh, well, to put it in context, that's fine. But it doesn't mean that the rate here is tremendously low. It's just that you're looking at a small volume of space. That's all.
I guess what is also interesting is that you want to know whether star formation is continuous or is it just coming into sort of a burst of star formation. There are two different ways that stars can also be formed. And it turns out the numbers that just Mark just talked about is actually very similar to also a star formation that you see on a larger scale for even the more massive stars, but they're even older. So that really says something interesting, that the star formation in the galactic center has been continuous for a long time. And that's an interesting way of really looking at it, rather than just thinking that the star formation is episodic, that it just happens every now and then, and you get a burst of star formation, and that's it. Things become quiescent for a while, and then again, a burst of star formation. But these numbers that are suggestive tell us that star formation really, it looks like it's continuous, and it's been going on for quite some time.
Well, that's counterintuitive, isn't it? Because it seems to me like there's to be a huge fight for resources at the center of the galaxy. You've got a 4 million solar mass black hole wanting all to eat everything up, and stars trying to form. Seems like it's a pretty sparse environment.
The stuff is falling in.
Well, so I would expect it would seem to me like you'd get it sporadically. Right now our black hole isn't feeding because there isn't.
But there is a
any.
Resupply. Alan is saying there's a resupply.
Yeah, I know that's what I mean. It's just kind of counterintuitive.
But does that, while we're wildly speculating, does that mean then that the supermassive black hole has been quiescent for a while? A long while.
I mean,
depends what time scale. Yeah. Go on.
Since we get to speculate, now we're on to the fun part. I mean, it seems to me you've got these 100 stars that are a few million, a couple of million years old, but seem to be roughly the same age. And so, you might get something like that happen every few million years. We see these low mass stars a little further out, which is a completely different mode, the way these things formed, but it's giving you a similar amount of mass per year on average, but that might happen more continually. It's all about supplying the gas to the center, right? And how that comes in from further away and falls into the central few parsecs of the galaxy. And then how does that gas get processed? So given that gas tends to come in lumps, you might expect things to be a bit sporadic. Plus the feedback, that we've talked about, if you dump a lot of material onto the black hole, then you will get a burst of activity that could clear out the region a little bit and hit the reset button. So it might be here that, that population, a million or so solar mass stars, is kind of you're looking at the granularity of this process that gives you a puff every few million years that makes the black hole active briefly and then clears out the region.
Okay, Carl, you want to get us some more questions? I see there's some more popping up here. Oh, did I get you doing something else?
Sorry about that. So there's a couple more that I think would be good to close us out with. There's a question from Oh my God, dog. Can can we tell stars are born together because the link between their metallicity, are whether or not they're composed of the same stuff? Couldn't we use that to tell if the stars were born there or traveled there to one extent or another?
That's related to what I asked earlier about how do you know it wasn't a captured star versus having formed there.
But is I guess one thing that I was wondering about kind of along those lines was like, are we able to observe the metallicity, or is there just too much disruption with other signals?
Anybody? It's hard. I'll let someone else go. I've said enough recently. So.
No, I just wanted to say that metallicity is a difficult measurement to make, and people have been doing it for quite some time. It's not clear what really lines one should go for to get a total metallicity. But generally, gas phase metallicity is higher in the galactic center. People generally consider that it's probably 2 or 3 times more metals are in the galactic center, in the interstellar medium of the galactic center. And it's, just because perhaps due to reprocessing of the gas going through lots of star formation, you see a higher metallicity. But it is, we definitely need more measurements to very close to the black hole to figure out what the metallicity is for these clouds.
Okay. And metallicity, folks, that's just that's a measure of the atoms in a star that is not hydrogen and helium, right? I mean, these are other heavier elements besides those two. Astronomers call them metals. Don't ask me why. I don't think they really know. They just do that. They call them metals, but they're not really like actual metals that you find in there.
So I think Achilles has asked like 3 different ideas that I want to steal for like a graduate dissertation in astrophysics. But his question is, say we have a star that forms around the black hole like the one that y'all have. Is there a mechanism that these new stars could get distributed into the galactic bulge, and might that be a link to the size of the supermassive black hole and the galactic bulge? Super speculative but awesome at the same time. I know.
Well, you can. If someone else can go. Yeah, no. All right. So it's hard work kicking a star out. Something that's kind of close in some kind of orbit, and then getting it on much further away from the hole. So you have to give it a kick. So one way is if you've got stars that are binaries that interact with a third star, you can exchange energy and kick one out. It's not that an efficient process, so I think it would be hard. I mean, you'd have to check the numbers, but my guess is it would be very hard to make up an entire bulge from close-in star formation, kicking stuff out. So there's probably a different reason for the correlation, I'm guessing.
Well, also, I thought that bulge stars were not as metal-rich as the stuff in the disk anyway. They are, for example, globular clusters that are in the bulge are slightly more metal-rich than the globular clusters in the halo, but they're not solar metallicity. So the bulge isn't really made of high metallicity stars that were ejected, by and large, from the black hole.
Mm-hmm.
I actually know something about that.
I think actually the globular clusters is a good point, because, how are you going to kick stars out and make a globular cluster? And the globular clusters are a bit big to make close into the black hole and kick them out and have any kind of cohesion. So that would be another point against that idea, I think. So.
And then David has what seems like a very wonderful technical question. Is carbon monoxide reliable as a tracer for helium, helium-2+, and H2? Might there be different ionization paths due to nuclear mass differences inside magnetic fields in the ISM?
What?
In the interstellar medium.
Who asked that? That David Sims?
David.
I didn't reliable that. Is CO2 reliable as a tracer for hydrogen, H2+, and molecular hydrogen? Do you understand that question, guys? Is it a good tracer?
It's
I
pretty
think,
good.
the question is, if you look at carbon monoxide, do you also know that there's hydrogen, helium, and other? What else do you think is there?
Got it. Good question.
It's a good tracer for all that stuff.
Okay. All right.
I think that's the question.
We use carbon monoxide to trace molecular hydrogen, which we can't see. But there's always a question about what is the abundance of carbon monoxide relative to H2.
Got it.
Seems to be pretty constant. But
okay. Good. Well,
good
thank
question.
you on that. On that question, we're going to have to stop because it is 4 o'clock. We are done. So there you go, folks. We now know that there is strong evidence that stars can form within the close proximity of a black hole, in particular within 3 light years or so of our own Sagittarius A-star black hole. And so more coming out all the time about this particular black hole. Carol, I want an Event Horizon Telescope hangout next year, if we can make that happen.
Maybe Al can help us do that.
Yes, because that's very exciting work.
We'll put you on tap for that.
All right.
I'm sure you can get in line.
Oh, come on. It's just an hour.
Yeah. Well, I hope, I'll be keeping track of that pretty closely, and hopefully we'll be able to, I don't know, get something out when the results are finally published on that, and we're all going to hear about it. You can be sure. Okay, folks.
We all want to see that.
I want to thank my guests. This has been a great discussion. I want to thank Dr. Farhad Zadeh from Northwestern University, Dr. Mark Wardle from Macquarie University down in Australia. Thank you, Mark.
Thank you
for staying up or getting
that bad.
Oh, good. And Dr. Al Wootten from the National Radio Astronomy Observatory. That's it. That's it for this time. I think we're done this year, right, Carol? Or do we have one? Okay.
Yes.
So
Happy New Year.
Yeah, we'll be back early.
Thank you for having us. Take care.
Yeah, thank you guys for showing up, for being here. We will be back early on Astro Coffee Hangout. I think we might have a Future in Space next week. I'm not sure. Talking to Harley about that. But otherwise, the AAS is coming up. Their big meeting in January. Maybe Carol and I can do something to talk about that. But we will be back early next year and pick these right back up. Thank you all so much for joining us. And have a great holiday season, if I don't get to say it beforehand. And thank you all very much for watching. And as always, keep looking up.
Thanks, everybody.
Keep looking up.
Okay. Goodbye.